Hi everyone, I'm Daisuke Iizawa from the University of Tokyo. I'm here to present the work Face on a Globe, a spherical robot that appears lifelike through smooth deformations and autonomous movement. Many domestic non-anthropomorphic robots are designed to be optimized for task execution. At the same time, with the spread of natural user interaction, there is a need for designs that improve affinity in social interaction. Some non-anthropomorphic robots have partially added anthropomorphic elements such as eyes and mouths. However, there are many previous studies of non-anthropomorphic robots in HRI's research. Moreover, those studies refer to Haida and Jimmer's animation of geometric figures, Reeves and Nass's media equation, and Dennett's intentional stance. With these references, we thought we could increase their affinity in social interaction without using anthropomorphic elements. Our goal was to create a non-anthropomorphic robot that switches between two different roles, such as domestic products and social robots. So, we designed a robot that can deform a part of a sphere to create a flat surface. We intended this flat surface to remind us of a human face. This idea is based on the following phenomena and studies. Pareidolia, the phenomenon of recalling faces from natural objects. Preference for face-like objects observed from 0 to 2 months of age. Blank faces in the classification of robot faces. And abstract art approach. Finally, we wanted to connect the two forms by smooth deformation and at the same time achieve a gradual increase in lifelike impression. This is the first robot we developed. In the design process, first, we use the computer graphics to check the deformation motion. In the next step, we use the 3D printer to check the smooth movement of the mechanism. Finally, we use the CNC to create a high-definition prototype. Each part of the deformation mechanism is made by cutting out a sphere in concentric circles from zenith direction. The mechanism creates a flat surface by moving each ring to the position where the top edge is aligned horizontally. Each ring has rails on each side. The pins fixed to the outer ring ride on the rails of the inner ring. By repeating this structure, all the rings are combined. We designed a height difference at each end of the rail. The relative height of the ring changes as the pins move over the rails by rotation. The rotation of the rings proceeds one by one in a chain reaction. This deformation mechanism has the following advantages. First, since the external parts and the mechanism are integrated, the internal space of a robot can be used widely. Second, only one motor is needed for deformation because it uses a chain of rotation. The last and most important characteristic of this mechanism is its smooth deformation. The following factors achieve this smoothness. First, the surface area of each part is small. Secondly, the amount of movement of each part is also small. Third, a chain of rotation and gradual deformation. Finally, the rotation and shading should not be noticeable. Evaluation. The setup of exhibit was as follows. The user could change the speed of deformation by dial operation, When the dialing stopped, the robot started to deform. The purpose of evaluation was to collect a wide range of impressions of a robot through free descriptions. As a result, we extracted 100 valid comments from 114 male and female participants ranging from their teens to 60s. We used text mining to create a co-occurrence network diagram to capture the comments objectively. As a result, it became clear that the words lifelike co-occurred with the words motion and smooth. Typical comments that included these words were as shown here. All the comments were written in Japanese. We have translated them into English after the analysis. Therefore, we have to note that lifelike is used as an expression for living thing. In the next iteration, we added autonomous movements to the robot to increase the lifelike impression. This is the second robot we developed. The rotation mechanism we added to this robot is as follows. Only the internal mechanism has been changed. The center of gravity is shifted by rotating the weight. It rotates and stops at the angle of the internal weight. It estimates the sound direction with 2 microphones. We conducted comparative evaluation of deformable and rotational model to check the lifelike impression of robots. We set up an online evaluation page with videos of each robot in action. Then we asked the participants to rate the robots on a 5 scale for each of the following impressions: lifelike, human-like, artificial, and intelligent. The results showed that the lifelike impression of the rotational model was significantly higher. To summarize, I will describe the contribution of this project and future challenges. The first contribution of this project is the creation of the concept for a non-anthropomorphic robot that changes lifelike impressions. The second is the development of the smooth deformation mechanism to increase the lifelike impression. This feature of the mechanism allows us to switch between the 2 different roles of the robot, such as domestic products and social robots. Future works will be application of non-anthropomorphic robots that changes lifelike impressions, or applications of our deformation mechanism to other purposes, such as moving mechanism or interactive part of the robot. Thank you for watching, and you are free to contact me if you have any questions.